Hello, my name is Brian Arders, and today I'll be discussing indium, a lesser known but critically important metal used in modern electronics. Although indium is not commonly talked about like iron or aluminum, it does play a key role in technologies we use every day, like smartphones or solar panels. In this presentation, I'll briefly explain its properties, how it is extracted and refined, how it is processed into usable forms, and I will also give two specific examples of finished products that rely on indium. Indium is a soft, silvery, white metal with an atomic number of 49 on the periodic table. One of its most notable properties is its extremely low melting point, approximately 157 degrees Celsius, which is much lower than most structural metals. It is also very soft and malleable, meaning it can be easily deformed. Indium has good electrical conductivity and forms stable compounds with oxygen and tin. While it is not used for structural applications due to its softness, its electrical and chemical properties make it especially valuable in electronic and thin film technologies. Indium is not typically mined directly. Instead, it is most commonly obtained as a byproduct of zinc ore processing. When zinc ores, such as sphalerite, are refined, small amounts of indium are present within the ore. During the zinc refining process, indium is separated from other elements through chemical extraction and precipitation methods. After the initial separation, the material must undergo further purification, often through electrorefining, in order to reach the very high purity levels required for electronical applications. Because indium production depends on zinc mining, its global supply is tied to the demand for zinc, making it a secondary metal in terms of resource extraction. One of the most important industrial uses of indium is in the production of indium tin oxide, commonly abbreviated as ITO. ITO is a compound made by combining indium oxide with tin oxide. What makes ITO unique is that it is both electrically conductive and optically transparent. These two properties are rarely found together in materials. Most conductive materials block light, and most transparent materials do not conduct electricity. ITO is typically applied as a very thin film using deposition processes such as sputtering. In sputtering, high energy particles are used to deposit a thin, uniform layer of material onto a surface. The thickness of this coating is precisely controlled to balance electrical conductivity with light transmission. A common finished product that uses indium tin oxide is the modern smartphone touchscreen. Capacitive touchscreens rely on a transparent conductive layer to detect changes in electrical charge when a finger touches the surface. The ITO layer forms a transparent electrode grid beneath the glass. When a user touches the screen, the electrical field at that location changes, allowing the device to detect the input. Without indium-based ITO, it would be difficult to create a screen that is both responsive to touch and visually transparent. Indium tin oxide is also used in certain types of solar panels as a transparent conductive electrode. In photovoltaic cells, light must pass through the top layer of the device in order to reach the semiconductor material that generates the electricity. The ITO layer allows light to enter the cell while simultaneously collecting and transporting the electrical current that's produced. This combination of transparency and conductivity makes indium-based coatings critical for efficient solar energy systems and other Optoelectronic devices. Despite its usefulness, indium presents some engineering challenges. Because it is primarily a byproduct of zinc refining, global supply is limited and dependent on other mining activities. Additionally, ITO coatings can be brittle. This creates challenges for flexible electronics and bendable displays. As a result of this, researchers are actively exploring alternative transparent conductive materials, but indium remains one of the most widely used solutions today. In conclusion, indium is a critical but often overlooked metal in modern technology. Although it is soft and not suitable for structural applications, its electrical properties and ability to form transparent conductive coatings make it essential in smartphones, solar panels, and other electronic systems. From extraction as a byproduct of zinc refining to thin film deposition in advanced devices, indium demonstrates how specialized materials play a major role in modern engineering. The information used in this presentation was supported by data from the U.S. Geological Survey's Mineral Commodity Summary on indium, which provides details about extraction, production, and global supply. I also reviewed solar energy materials and solar cells to better understand its manufacturing processes and applications. These sources helped ensure the technical accuracy of the refining methods and finished product examples discussed. Thank you for watching and listening. I did use AI to help me with this presentation. I used ChatGPT to help me understand information and also to build the script. I found it to be helpful to streamline the presentation making process and understanding some of the key aspects of indium.